we're gonna start a journey of some math, and I'll try not to drown you with lots of equations. I mean, it's gonna be drowning, but still I try to keep them as much as possible. Then I want to jump to the coding and tutorial relatively quickly, right? So here are the contents. Again, I'm gonna give some reminders about generative modeling. Then I'm gonna introduce what are latent variable models, which is a new term maybe for you, which are very important for variational autoencoders. Those are the core principles of the variational autoencoders. And lastly, we're gonna jump into hands-on session. Yep. So maybe you remember this figure. Maybe for the people who are not maybe in the first part, we want to model a probability distribution, which is as similar as a real-life probability distribution that we cannot observe. And we only have data, and the data is also a probability distribution, an empirical one, and minimizing the KL divergence between the data distribution and the model that we have results in maximizing the log likelihood, which is actually indicates the coverage of our model of our on top of our data set, right? Great, it's great. But then, okay, like we also have this problem with the high dimensionality. There are lots of parameters required for modeling the relations between the features, dimensions, etc. So it's very unscalable. It's a nightmare, even for the deep neural networks. So one idea to overcome this is latent variable models. So the idea is, by the way, sorry, maybe I can do something like that for the physical attendees. Yeah. So idea is we introduce something new, an unobserved auxiliary variable called latent variable. We don't know what it is. It can be fictive, it can be real. We don't observe it, but we assume it's there. So generally, we tend to model this latent variable with a dimensionality way less than the observable ones. Here, our observable variables are like x1, x2, x3, x4, etc. And it's a vector of x, and it's d-dimensional. And we have a latent variable called z. And this z is m-dimensional. And generally, this m is way less than this d. And as you can see, most of the time, still, it's not the only way. But we say, okay, this is the connections. But if we knew what is that, these x's, the observed features, variables, they become independent, which is a very well-established method in the probability domain. Maybe you use it already in your studies because Kalman filters is a latent variable model. You can check later in the Wikipedia, but it's a very well-established model which makes our life easier. Actually, you can, for the control people, you can think about these x's as y's in the sensor output, and that are the states that you cannot observe all of it, right? You can think like that. So we say some math, sorry, but yeah, it's actually the easiest one. So like that. We are looking for this, right? But we say it's super complex and it's hard to model. Then we introduce a variable called z. So we have a joint probability density function, pxz. And if we take the integral and marginalize it, it still holds the equation, right? Okay, great. Then it's like px given z times pz. So pz is here. And we say that here's the biggest assumption. If we know the pz, px given, sorry, if we know the z, px given z becomes independent, and the multiplication is basic probability, right? And the motivation is, again, as we discussed in the break, meaningful data tends to reside on a lower dimensional manifold in high dimensional spaces, right? And we say, or maybe because like, we say this z can help to move in this on this travel around this manifold, because this manifold is way less dimensional than the original observable data point. So this z can help us. It can navigate us in the lower dimensional manifold. That's one. Secondly, if we go into the probabilistic modeling with the expert-based knowledge, it's a bit ancient now, but still like psychologists and everyone like in the soft sciences part, people tend to use this kind of things. If we know some causal relations, this can simplify the model. For example, you're a psychologist, and the patients had like fatigue. I'm sorry, you cannot see, but I'm just gonna tell, like fatigue, loss of interest, insomnia, suicidal thoughts, etc. And these are super related things, right? They affect each other a lot, and you can basically measure them with testing. But if you knew the depression level, these become uncoupled, right? If you know the depression, you can assign a fatigueness level. If you know the depression, you can assign the insomnia. But you don't know, you cannot test the depression, right? So generally, I mean, it's a bit of a spoiler. Generally, we want to actually infer depression level by looking at the observable variables. But again, depression level is a fictive thing. We just came up with something like that. And it's the same thing right now that we're going to do with smart meter modeling. It's not going to have exact meaning, but still, it's going to make our lives easier. Then, just one example. I don't want to give lots of examples in this. Gaussian mixture models. I don't know how many of you knows this, but Gaussian mixture models basically average of more than one Gaussian distributions in a one-dimensional, arbitrary number of dimensional spaces. And if you use any, if you use many distributions, Gaussians, you can converge to any distributions, right? But it's like a general approximator, as Conrad said. For example, it's a weird distribution, right? Does anyone know this kind of a 2D distribution that explains this kind of a behavior? No, because it's like it can be anything. It's like a weird behavior, right? And this weird behavior requires Px to be expressive enough to capture these nonlinearities, this interesting behavior. And this is like only the X, right? We don't see also the third dimension saying the probable density likelihoods, right? And we say, okay, instead of focusing on Px and how come up with a very complex model or like neural networks or anything to model this weird thing, we can just come up with like, okay, let's have 3 Gaussians and find the means covariance of those and assign some sort of a weight for all of those, because these are the occurrence probabilities of these blobs. Let's say now they are blobs, of course, I revealed, but they are not the same, right? So we say we introduce the PZ that indicates which cluster or Gaussian blob we are going to choose. So this is one blob, and let's say this is Z1, Z2, Z3. So if we know it's like it's coming from this blob, which means we observe Z1, we never observe, but still. We say, okay, after we know that is one, it's basically a Gaussian, and it makes our lives super easier. And you can, and this framework help us to find efficient modeling for this thing. And Gaussian mixture models, like they have really nice closed form formulations, iterative expectation maximization methods for optimizing this thing, and they are amazing. But of course, they are very limited because they are Gaussians at the end of the day, right? And you don't want to use lots of components because then it would be inefficient. So, what are variational autoencoders? Some background. First of all, they are great. They are introduced in 2013. In 2013, there were 2 papers doing the similar things. And whenever you see like a proper computer science paper, like using variational autoencoders, they generally cite 2 papers, but this is the paper that coined the term. This is a paper never published anywhere. It's just an archive preprint, sorry. And it has more than like 35,000 citations. I hope the message by some people works. Yeah. 2 interpretations for this kind of models. It's either you can think it is a probabilistic autoencoder. I don't know what do you know? I don't know if you know what is a autoencoder is. But we're gonna focus on a latent variable model parameterized by neural networks, right? So back then, like in the Gaussian mixture model case, there were no neural networks, right? We had like the data mean parameters for each clusters and the covariance. But if we want to find different relations, and of course, like limited number of blobs. Now imagine these blobs are like infinite, continuous, and these center and covariance parameters are parameterized by super large neural networks. So first, I'm going to give you the end result of this variational autoencoders before diving the heavy math. And now you can just think about it. Magically, we ended up with this loss function, which looks like weird, right? Magically, we ended up this loss function, and it works. Okay, let's just think about it for a moment. So we have 2 neural networks. One of them is the encoder, takes the input x, high-dimensional input x, maps it to one mean parameter and one standard deviation parameter. And of course, it can be any distribution, but we're just talking about Gaussian distributions right now. So it's just mean and standard deviation is enough to model represent a Gaussian distribution. Then we take a sample from this Gaussian distribution, Zi, right? This is our latent variable that we observe. Okay. We try to learn this latent variable. You can think like, okay, this network takes like inputs like the insomnia, suicidal tendencies, etc., lots of things, and tries to give a depression score, right? Then, by the way, this is only for training, right? If you want, after training, of course, you can either only use this for understanding the data, or only this, as I'm gonna explain now. This is another neural network decoder, takes the Zi and reconstructs or samples a data point, which is the main part of like that we're interested of synthetic data generation. But this is also very promising for lots of applications because it's like a dimensionality reduction. So this reconstruction again is a Gaussian distribution, but we generally are going to use, we tend to use only the mean as the reconstruction of this Gaussian distribution. We don't take samples again because lots of reasons, we can discuss it later. But this is the framework. So there are 2 objectives. We want a good reconstruction. We want to replicate whatever we have in the input. so that this pipeline first embed some information about this xi to zi, and this decoder reconstruct, or retrieves that information from zi and builds xi, and which is actually like a underdefined kind of problem, because there's an information bottleneck here, right? Most of the cases. So we say xi's, the reconstructions should be as similar as these inputs, so that i's holds important information about xi's. This is one thing, that I should hold information. But at the same time, that i's, given the xi's, this latent encoding, the encoding should be as similar as possible to a prior standard normal distribution, so that i's holds important information about other data points too. It doesn't only hold information about that exact point, but also other points, hence the generalization, okay? Because if we didn't have this regularization, it would be a basic autoencoder. And the basic autoencoder means no generation, or data generation capabilities. Then we have this term for the reconstruction error that we want to minimize, but we also have this regularization term. Sorry, we have this term. We want to maximize this loss. Loss is a wrong term, but it's an objective. We want to maximize this, so minimize the reconstruction error because there's a minus here, and with a regularization so that we don't overfit to the data, right? So some math. I don't know if I should cover all of these or not. Let me check the time. Maybe a little bit if you're interested. I already talked about this latent variable models. This is the marginalization that we want to achieve. We call this Px given z, which is the decoder distribution. We call this like the likelihood or the inference model, where this can be very flexible, can be modeled with a neural network. Please be aware that this is like a low to high mapping, which is a very different thing from the usual machine learning things, because generally you take a large input and try to estimate one output, or either a class or a final output for regression, but it's a different thing. PZ is like they call the prior. That is the sort of a regularization term. You can transfer some prior assumptions using the model, but in practice, since you're generally data agnostic, in terms of model development, this is set like standard normal distribution. I even use that like that. This is the averaging over latent variables, marginalization. This is impossible. This integral, taking integrals over neural networks is impossible, okay? So we cannot do it analytically, of course, and it's extremely expensive to do it numerically. So we need a different thing. Then we define also a prior distribution, posterior distribution. This is exactly what I talked about. If I see the insomnia levels, the suicidal tendencies, etc., we want to assign a likelihood to depression, for example, right? So this is the formulation for that. It's the basic Bayesian equation, Bayes rule, but still it contains this filthy integral that we cannot do, right? So we cannot achieve that. So instead, we use, and this should be red. Instead, we use an approximate posterior called Q5 ZX. That's exactly the encoder that I showed in the previous slide. As you can see, it's the same index. It's up. This is the approximate posterior. This is the likelihood distribution, the inference. Yes, that's the mathematical definition for these models. And so, as I told, we want to maximize the log likelihood, but we don't have this px. What should I do? That's one of the best, I think, derivations in the machine learning community. We just multiply and divide by the approximate posterior. Since it's logarithm, we take it out, these things. And then we take an expectation of this q phi z given x. Since it's expectation is the integral, right? And it depends on z. So, but this is all depends on, sorry, this all depends on x, right? So it doesn't affect, so this holds, right? It's just the integration which without the variable. Then we just distribute this expectation. Then we have this reconstruction term, which we call reconstruction log likelihood. We have two log KL divergences. One of them is the discrepancy between approximate posterior and the prior, which we choose. And the other one is the discrepancy between the approximate posterior and the true posterior, which we cannot calculate. So the only part, sorry, maybe I should go back. Sorry. KL divergence is always positively defined. The only part that we cannot calculate is this, the last one, right? And we know KL divergence is always positive definite. So this is always positive, this is always positive. Sorry, this is always positive, this is always positive. So we can lower bound it. Great, right? So we just get rid of the thing that we cannot calculate. We lower bound it, and it's always lower than the log likelihood. And we call it evidence lower bound. So we say that if we maximize this evidence lower bound, we're also maximizing the marginal log likelihood that we want. Great. So we ended up with the first reconstruction success, let's say, and the KL divergence terms. Then, how to implement and train VAEs? Here's the recipe. First, we have to select distributions. It totally depends on the application. It can be Gaussian, log normal, beta distribution, categorical distribution. Depends on what kind of data you are handling with, or dealing with, right? 2 theta z x, the approximate posterior, the encoder distribution, is also free of choice. Pardon, sorry. This is not free of choice. This depends on your data. This can be definitely free of choice. Generally used Gaussian, that's why. But there's one thing, it should be, it's better to take samples from it in a straightforward manner. I'm gonna come to that. And PZ is also like a sort of free, but since we have this term, it's better to have an analytical result for this KL divergence. So we have this reconstruction log likelihood. If you open it, there's a expectation here. So we don't have a closed form expression for that. So we can use Monte Carlo approximation for that. But then if you take Monte Carlo samples in the neural network training, then you cut the gradient pathways. So you need a better way for sampling. Then there's this reparameterization trick. I'm not gonna cover it all, but generally Gaussian distributions are enough for this, right? So it's representative enough. KL divergence, if we use standard normal for our prior and Gaussian distribution for our approximate posterior, or encoder, we can derive the exact KL divergence, which is great. And if we put everything together, we have a reconstruction error and a KL divergence. And if we replace all the parameterized functions with neural networks, we end up with this, which is the first image. And then, since we have the objective function, And and the neural networks just take your favorite deep learning library and it does its magic. It's pretty straightforward. I'm not gonna investigate the overall elbow that much. We can talk about it if you want. So one important remark. We use the prior distributions for two reasons in practice. Of course, regularizing the latency encodings during training, so it's important for training. And also, in the generation time, we take, if you remember, I cannot go back, but if you remember the marginal log likelihood, we had an integral, px given z times pz. So there's no approximate posterior. So we only use the prior distribution for generating data because we don't have the actual data, of course, for their latent encodings for generation. So some examples. This is the most well-established data set in the image processing community is MNIST, like the handwritten data sets and handwritten digits data sets. As you can see, these are the original data points trained with after it training using this a variational autoencoder. These are the reconstructions of this. So we input these into the encoder. We take a sample in the latent space. We decode it, and we get this. As you can see, they are pretty similar. Do we want them to be really very similar? It's a question to be answered, but they are similar, so it works. What about the samples? These are all samples from, we take random samples from the prior latent space, let's say, and decode them, and we get this. So these are the data points. Hopefully, they do not exist in the data set. So these are novel. So we generated new data points. What about harder data sets? This is a Telebay data set, and there are lots of celebrity faces inside. And again, the same procedure. Originals are these. And these are the reconstructions. These are sort of blurry. If you look at in detail, these are blurry. This is one of the drawbacks of the variational autoencoders. They tend to smooth out the data, but the most informative parts, as you can see, is pretty detailed, which is the most of the time important part. What about the synthetic data? As you can see, samples. I mean, this is of course like a super powerful methodology right now that you see. I mean, this is like from 2014 or something. But still, for that time, it was super promising, right? Like, because, you know, you can generate some realistic human faces just from the data, and you don't do any image processing or anything. Even I could do this. I could do it, you know, as a control engineer in my master's. I was dealing with this kind of data, and I was not an image processing guy because all the image processing was basically going in the neural networks implicitly, which is an amazing thing. So I have to talk about some extensions. Actually, one of them called conditional VAE. We talked about PX, probability of X, but most of the time, as engineers, we have some conditions. And what are these conditions? These are additional information which are not random. In this case, for example, if you want a model that generates the given digits, you have to model px given y. Y here is the digit label, right? So if you put this y here, everything stays the same in terms of derivations. You just concatenate this y to x and also z. That's pretty much I'm gonna show. And if you have this extra information, as you can see, it gives another layer of controllability. Now you don't take like wild guesses about what to generate. If you want to generate zeros, you can generate different zeros. If you want to generate ones, you can generate different ones, which is very powerful. So for the hands-on session, we're gonna use daily snapshots. As I told, we're doing some profiling. We have we have a data set, open data set. I'm gonna share the GitHub repo. It's an open data set from only one customer. It's like 1 year of data, I guess. And we take daily profiles, not 1 year, I think a couple of years. We get daily profiles and hourly resolution, right? So every data point is a 24-dimensional vector representation. Okay. What about the conditions? We use basic conditions as months and days of the week, which are like Sunday, Monday, Tuesday, etc. And since these are like, okay, these are categorical variables, but at the same time, they have some information, right? So however I act in June, it's probably very similar in July, right? Maybe not exactly the same, but it's gonna be similar. And also, since they are like, there's a transition from December to January, they are circular. So we can apply some circular transformation, right? We can order these months, also like the days of the week, in a polar coordinate, and we can represent these months and weekdays as 2-dimensional vectors. And we end up with this. So these are our inputs. In this case, I think I have a slide from like half-hourly data set, so that's why it's like 48. But in our case, it's I think 24. We have our conditions. We have our latent encoding, and again we have our conditions. Okay, great. And then here's the pipeline. So that's all before the hands-on session. Does anyone have any question? I know that was a lot of math, but very few of those are super relevant to the hands-on session. So before diving into it, does anyone have any question? Okay, great. I'm looking at the chat also, no? Okay, great. So here's the QR code, but since you're on your laptops, you can just go to this repo. My repo, actually, Kutay Bölat, and then you can find this InnoCyPES Summer School Synthetic Data tutorial. And for this, I'm stopping sharing. From there, maybe I should better to share my. So first, let's go to the repo. Yeah. When you go there, you're gonna see this. And in here, there are some explanations and everything. You can always download the repo and run in your own local machine. But I know it's a bit of a hassle. So there's a Colab notebook link here. And here you can find the whole notebook, right? The exact notebook that I'm gonna use. Actually, there's a bug, but I think you already don't have. Yeah, if you experience a bug, just let me know. But it should be fine. And I'm gonna do everything in my own local machine. And for the time, yes. So first, we have some libraries. It's not important. We download the data from this UCI machine learning data repository. There's a household power consumption data set there. It's not a super good data set, but still it's nice to showcase things. We first pre-process the data. It's like the profiling part. No, sorry. First, we set the resolution. It's not that important. We end up with this kind of data, and we get the months and weekdays here. And and we end up with profiles, right? Are there any questions until this point from the data preparation part? I think it should be pretty obvious. Then we define a PyTorch dataset. In this case, it's like electricity data, and we have these conditions to circularize things. Then we define our neural networks, our encoder and a decoder. So one problem, so since we work with probability distributions, and these probability distributions are, in this case, Gaussian distributions, are parameterized with mean and standard deviation or variance. Mean is okay. We can just put Z and take an output. But for the standard deviation, we have to be ensure the output is positive. So we apply a transformation for that. So we take the outputs of a neural network. These outputs we call like sigma tilde. And we apply this transformation. It's some sort of a soft plus transformation, which has an inverse transformation too. And we end up with positive outputs, which is important. And then we define our VAE. We have we set our number of layers. You can change all of this. Whatever you see in capital letters, you can change it and try it for yourself for different settings. So for this case, the number of layers are 2 both in the encoder and decoder. So we have 4 layers in total, and number of neurons for each layer is 500 to keep things simple. Then here's the training settings. Of course, you have to choose how many latent dimensions. What's the dimensionality of the? Can you see it, by the way? Sorry. How many latent dimensions for the Z, for the latent encoding? In this case, I chose 5. So it's a 24:5 mapping for the encoder. There's a beta. Don't forget about it for now. It's like a weight for the KL divergence term. We're gonna set it to 1, and the rest is basic neural network training parameters, base size, epoch, etc. The other thing is for the ablation study. So if you leave the condition index empty, you don't use any condition. It's a basic VAE. So if you put only 0, you're conditioned only on the months. If you put 1, it's only weekdays, and if you put 0 and 1, it's both. So I already run the training, and because it takes like 3 minutes, 4 minutes. It's a very small data set, but still I didn't want to make you wait. And it ran, and then we have to check how it performs, right? So generally, I showed you for MNIST dataset and Salabay dataset. First, we check the reconstructions and the random samples, right? Now check the reconstructions first, right? Reconstruction visualization. So for reconstructions, since we have a latent encoding, which is like a probability distribution, we can take lots of samples from it too, right? So in the examples that I showed, it was only 1 sample per reconstruction, but I'm gonna show you more than 1. So as you can see, the blue profile is the original profile, and the gray ones, because there are tens of them, are the reconstruction means. I told you the output is also a probability distribution, and the shadings around them are the standard deviations on the decoder, right? So we also have some sort of an uncertainty captured in the reconstructions. So as you can see, it's super good reconstruction, right? And you might say, okay, this is clearly overfit. And you might be correct. that's a thing to investigate. But it shows we are capable of capturing all the dependencies, all this profiling and everything with that kind of a 24 to 5 to 24 information bottleneck, which is great. So then we can see some latent visualizations, right? So I told you latent encodings are also probability distributions, which are Gaussian. And for it means for every data point, we have a multivariate Gaussian distribution. It's impossible to visualize, but instead we can map them to a two-dimensional plane. So for that, we did this. As you can see, the color codes are basically the conditions of individual data points. As you can see in the latent space, similar months tend to be closer, right? But by the way, this is like low dimensional projection, so we lose lots of information, of course, by doing that. But you can say, okay, like the winter times are sort of close to each other, like summer times are close to each other. But we cannot say the same thing for weekdays. So you can say, okay, weekdays are not that informative in terms of conditions, for example. And it's correct, right? So because it generally it doesn't matter if it's Wednesday or Tuesday. Maybe like saying if it's a weekend or not, or if it's like a holiday or not, is much more informative, right? There are nice. This is the part that you reveal some important information. And lastly, sample generation. We have our prior, and we take a sample from it. And by the way, like we also can see, sorry for that, but we can still do like a different kind of reconstructions, right? I didn't do different ones, sorry. As you can see, these are different data points from the data set, and you can see, okay, we mostly cover the original data point in our reconstruction, which shows like promising performance. And when it comes to sampling, we have a sample like this, right? And as you can see, by taking different samples from the latent prior, we can reconstruct or generate different kinds of synthetic data, right? Which is the most baseline case of the variational autoencoders for generating synthetic data. I also, how much do I have? Okay. Lastly, I also did some ablation study by using no conditions, only weekdays, only months, and only and both of them. And you can find them in the runs folder, and by opening them in the TensorBoard. Yeah, there are some instructions in the notebook. You can find it, but let's check the study the scenario that we don't have any conditions. So learning sigma false. Let's go with this. I also didn't mention. So the output distribution is a Gaussian too, right? So the Gaussians are modeled with a mean and a standard deviation, right? But we don't necessarily need to learn the output standard deviations. You can control it in the notebook if you want to train the output standard deviation or not. But the heads up is if you try to learn the standard deviations on the output, you're mathematically proven that you're going to overfit. Okay, if you train enough. This is the part, like this is the scenario that we don't learn using the we don't use the conditions. And as you can see, we try to, this does not look like Gaussian, right? Because we want to embed as much as information as possible, because latent space is also trying to hold information about the conditions, because we don't supply the conditions. If we learn the sigmas, as you can see, your latent space becomes like this. You try to overfit. It becomes like a normal autoencoder. You can see like how picky is this. Also, we can see these in the reconstructions. This is the reconstruction that we don't use any conditions, but we learn the sigma. You see, it's super. In this part, there is a really low uncertainty. But if we don't learn the sigma, as you can see, we're trying to be very generalizable. You know, like we actually underfit. And the similar happens for the cases that we learn with the conditions and etc. And same with the samples. Yeah, as you can see, our samples, if we learn the sigma, it becomes super sure about what's going on that region. And it's actually useful, right? Because most of the time we know that if from in the midnight to 5 a.m. there is no consumption that much, but it's much more uncertain in the morning and after work. But during the day it's also like not super uncertain. So learning sigmas can be very powerful, but you should be careful with the overfitting. So you can find all these results in the GitHub repository. I'm gonna share the slides in the repository too, and I think you can access them afterwards in the website. And I think that's pretty much it from my side. If you have any questions regarding the codes or like variational autoencoders, I would be happy to answer them. Thank you for your attention.